My name is Carrie Williams, and I'm the Marketing Manager for Test Oil. Today, we are pleased to present a webinar entitled Additive Reconstruction of Oils. Before we start the webinar, there's a few things I want to go over. First of all, I want to check my audio. So if you can hear me, please raise your hand by clicking on the little hand icon that's in the toolbar of your GoToWebinar application. I see a few hands. Okay, great. I see a few hands, so that means my audio is working. Now, the other thing I want to do is just let everyone know that you will be on mute during this webinar. We are recording this presentation so I can share it with you later, and by keeping everyone mute, it will ensure a high-quality recording. Now, if you have questions, please feel free to submit them using the questions field toolbar that's on the GoToWebinar application. It's just below the attendees where you were raising your hand. If we have time at the end of the webinar, I will ask our speaker your questions, but if we don't have time, we'll make sure we address those via email. So let's get started. Today's presenter is David Pinchuk. David is the co-founder and CEO of Thermal-Lube, Inc. It's a Montreal-based specialty lubricant, agriculture adjuvant, and analytical equipment manufacturer since 1983. Dave chaired the ASTM International Subcommittee on in-service lubricant testing and condition monitoring services, on IR and FTIR IR testing practices and techniques related to in-service lubricants from 2003 through 2011. Dave's been invited as a speaker, presenter, and panelist on numerous occasions with ASTM International, STLE, NORIA, McGill University, and several other organizations. So with that, I'm going to thank Dave for joining us today, and I'm going to pass the controls on to him. Are you with us, Dave?
I am with you, Carrie. I hope, thanks for the introduction, and I hope everyone hears me also. The audio is coming in clear. Am I okay? I guess I'm okay. All right.
I can hear you. Yes, I can hear you, Dave.
Okay, so I'm going to get started with this over here. Thank you. Just want to tell you that over here, I'm talking, we're in Montreal, Canada. Woke up this morning, it was minus 25 degrees Celsius, which is about minus 13 Fahrenheit, and we had a wind chill of minus 38 degrees C, which is about minus 36 Fahrenheit, and as you all probably know, the scales meet at minus 40, so it's pretty cold here this morning, and want to wish you a warm welcome to this webinar. A little bit more background on Thermal-Lube. We do maintain a government-accredited research facility focusing on fluid degradations in the lubricant, food, wine, and medical industries, employing novel infrared FTIR-based quantitative analytical procedures. We've also developed detection and recording devices based on FTIR for air quality monitoring, including the quantification of airborne particulates and pollution contaminants. We have, in this domain, we do have a patent on our FTIR itself, the way that we're doing our detection, but we have a new patent on the quantitative determination of acid number by FTIR, and we have patent applications in for the determination of base number and moisture using FTIR. A lot of the research that we've done is in collaboration with McGill University in Montreal and the University of Quebec in Chicoutimi, which is about a 6-hour drive north of Montreal, and we've published more than 60 papers in various industry media. So now that we have that sort of put away, let me go on with the additive reconstruction of oils.
Dave?
Yeah?
Can I jump in real quick? I've had a couple comments that we can't hear you. Can you speak up a bit louder?
Sure, I'll do that. Let me just move this. As a matter of fact, is this better? Okay.
That's better.
I was using a speakerphone, so now I got the speaker in my ear. So hopefully this is better. All right, let me just this over here. Sorry, we'll get this open. Okay, so talking about the additive reconstruction of oils. This is something which is, just 1 second, please. There we go. Okay, so why do we want to do this? Okay, for the additive reconstruction of oils, this webinar is going to be basically divided into 3 different sections. We're going to discuss why we want to do it, reasonings why we want to do it. It's not going to be highly technical. It's going to be a very basic type of opening up some new ideas and kind of thinking outside of the bottle or the box or the drum, where whatever industry you're into over here. So what we can do with this over here, we're talking about replenishing depleted additives from in-service lubricants. There are some actual legal definitions of difference between what's called new oil, in-service oil, used oil, and waste oil. So new oil is pretty well defined. That's new oil. In-service oil is oil that is already in your equipment, that's in service, that you can send out for analysis. Used oil is oil that's taken out of your equipment and it's stored in some sort of capacity. And waste oil is oil that has to be just wasted or disposed of. So within the ASTM in the last 5 or 6 years or so, we've kind of redefined the word in service and not saying, let's say, we're doing used oil analysis, we're doing in service oil analysis, because these are, as I said, oils that are being analyzed in service. Second point here is we can reinforce performance additives to alter fluid characteristics. Sometimes in some different applications, you may need some additional, let's say, antioxidant or anti-wear properties that are in the fluids themselves. We're going to jump into that a little bit later on in the talk over there. And we can re-additize lubricants after re-refining, filtering, scrubbing, dehydration. These additives seem to be, they can fall from the wayside, they can be filtered out, or they can be used up. So the raison d'etre of the whole thing is basically to reduce waste, to reduce your disposal, and to reduce your cost of ownership. And let's face it, the oil itself that you're using is already about 500 million years old. What's 1 or 2 more years added onto it? Doesn't really make much of a difference on the oil itself. But on the additives, this is something that we have to talk about, and this is something that we're going to look into. So why bother looking? Why bother doing it? Well, let's look at the big picture, which is going to be the first one. And the big picture, I think what we have to do is we have to understand where we are right now. I know we're all enjoying lower prices at the pumps, but let's take a look at globally why we want to do this over here. This slide over here, we're gonna look at the worldwide energy appetite. If you look at some of the data that we had, this I put together because 2014 wasn't finished yet, wasn't done yet. You can see that there's a definite rise in all these type of energy consumptions, and you can see that the oil consumption is up also. The oil use is up also. Okay, in 2013, the United States consumed a total of almost 7 billion barrels of petroleum products, and an average of about 19 million barrels per day in the United States alone. Looking at this chart over here and equalizing it over 100%, we can very clearly see that the consumption of oil compared to other energy consumption has gone down. So you can see there's more of a place for natural gas, coal-fired, and other sources of energy here, but there's still the lion's share of consumption comes from oil, And this is very, very, very important to know at this point. So what has happened between, let's say, 1965 and 2013, and we're talking about just in the United States. You can read this here to put the oil boom into perspective over here. From 1965, you can see that the U.S. oil production has gone down. At this point over here, in about 2008, 2009, fracking started within the United States and started producing some of their own products. Okay, so over the past 5 years, global oil production has increased by almost 4 million barrels per day. That's over the past 5 years. During that time span, the U.S. production increased by 3.2 million barrels per day, which was 83.6% of the total global increase. So you can see that even the United States economy alone has taken the lion's share of the increase in the amount of oil that is being produced on a daily basis and consumed on the daily basis. A little caveat over here is that should the shale oil boom never happen and U.S. production continue to decline, if this slope continued down towards this over here, the global price of oil might easily be about $150 to $200 a barrel by now. That would be pretty expensive at the pump. Without these additional barrels from North Dakota and Texas, the price of crude would have risen sharply until supply and demand were in balance. So it really put a dent in the global pricing of what we see now on the market with shale production in the United States. But when we take this a little step further, I mean, all this is fine and works pretty well, but let's just look at the actual capacity to refine oils. I mean, this is a huge bottleneck. You can have all the crude oil you want, but if you're looking at the number of refineries, let's say from year 2000, the amount of refineries is not going up. There hasn't been a new refinery built in the United States in the last 25 years. Some of the refineries are being augmented and expanded, but the actual overall capacity, you can see that the efficiency of some of the refineries has gone up. So really, right now, you're at the borderline of about 18 million barrels per day. And as we saw in a couple of slides before, the consumption is about 19 or almost 20 million barrels per day. I've seen it in the last couple of years was actually peaked up at about 21 or 22 million barrels a day. That balance has to be imported as refined products. So there's a limiting factor over here. As I said, you can dig your oils, you can refine, you can produce crude oils or produce crude oils or shale oils, but the limit and the bottleneck is going to be the number of refineries that you have in the United States at this point. So let's take a look at this. This is a really interesting slide from what I see over here. And you can look at this right now, and you can, this was obviously put together in May of 2014. This is before the price of crude oil started to crunch down. And we can see why this thing is happening over here. If we look at the Mideast prices, now these prices, the lines that you see across over here, this is a break-even price. Now, the cost that you see, for instance, on the onshore Mideast price there, $27 a barrel, this includes not only the lifting cost of the oil, but the exploratory costs. So you can't just say how much does it cost to take a barrel of oil out of the ground. That's obviously a lot less, and it's probably less than half what that cost is over there. But there's a cost of exploration that has to be added on to it. So if you look at the range of the cost over here, so this is the median cost of $27, but in reality, if you went down to about $9 or $10 a barrel, if you stop doing your explorations, well, this cost is going to drift down to your barest minimum that you have here. Now looking across, you're looking here, this is North American shale prices here, you're talking about $65 a barrel. And these are normalized, if you look at the y-axis, it's average Brent equivalent break-even price per barrel. So this is liquids production. Keep in mind, it's not just crude oil production. These are all equivalents that are equalized on the y-axis over here. And these are the amount of barrels per day that they can ship out. So when you're looking at prices now at hovering under $50, you can see that the North American shale prices are struggling a little bit here. RLW, that's rest of the world prices, about 51. Arctic, you can see, is pretty high. Obviously, the cost of exploration is very high, but you can see where this is trending to. So if the Saudis and the Middle East people are trying to keep the cost and the price of oil down, you can see how it's going to affect these people over here, because they may have to give up some of the exploration or drastically increase their efficiency to make it work. And fortunately, on the U.S. market, they are drastically increasing their efficiency. So this average cost of $65 is actually trending down a little bit, but we still got a far way to go if you want to get down to $27 at that point. So this is kind of like a snapshot of what we have today. Let's kind of click to the future a little bit and take a look at what's there and what's not there. So estimates that we have now, okay, based on the technology that we have now, and estimates that there's about 1.7 trillion barrels of crude oil still left untapped. Okay, now this is always a crapshoot, because many people will dispute this number, but there, and I've heard figures up to 7 or 8 trillion barrels of crude oil that's left on tap. It may be true that there's 7 or 8 trillion barrels of crude oil that's left on tap, but if it's going to cost $400 or $500 a barrel to bring this up to the surface, how relevant is that going to be to our lifestyle as it is right now? So the $1.7 trillion of crude oil that's still left untapped, let's just go with this for a bit. And if we're going to take a look at the in the year 2014, the annual worldwide oil consumption, okay, is about 92 million barrels per day. This is what the this is what the actual consumption is, all right, which is 33 billion barrels per year. That's a lot of money. I think normally when you were talking up around the billions and trillions marks, everybody thinks of military budgets and spending, but this is a lot of money. When you look at the if you want to basically take a trend based on 2014 consumption, and not even the increased consumption that we're getting, let's say, over the last 5 years, but let's flatline it and say that we're going to take the 1.7 trillion barrels and divide that by that we have left. So we basically have about 50 and a half years of supply left based on the technology that we have today. If we're going to take a mean average of that over there, let's say we have at least 25 years of good oil supply based on today's technology and today's type of costing. So something's going to have to give within the next little while, and this kind of like leaves food for thought, thinking outside of the box. What are we going to do, and how are we going to move forward with this here? So that's kind of a global picture that's out over there, and it's kind of gives you a perspective of where we're going in that direction. So we looked at the big picture over there. Let's take a quick look at the technology. Not knowing basically who the audience is out there in the webinar, I'm going to give you a very quick synopsis of what happens to the oil on a refinery basis, and how we move ahead and even blend some lubricants. So let's take a look. We have this is an atmospheric distillation unit over here. You have crude oil that goes in one side over there. Different weights. You have your bitumen that kind of comes out at the bottom, so this is good for asphalt and tar. You get some atmospheric fuels. So this comes out over here in different fractions and viscosities. So all these, you got little balls, big balls, and whatever. And if you squish them all together, you come up with something that's called a mineral oil. You have your gas oils, you have your naphthas, and you have your other gases. So there's different fractions that come off of the crude oils. Now, obviously, there are different types of crude oils that go in there. So this mixture may be a little bit different. So this is a very, very quick synopsis on crude oil conversion to a lubricant. If we take it a step further here, and we talk about synthesizing a lubricant. So here we can basically take a molecule, okay, which is a simple molecule that we have over here, and we spin them in together. We make this one decane homopolymer, and some of you, or some of us, we call that's a polyalpha olefin or a PAO. And in this case over here, all the molecules are the same size. And the difference between the molecules of the same size and having mineral oils, which are molecules of different sizes, this is easier to predict the characteristics of the oil itself. And plus, if you kind of want to think of sandwiching this between two boards, they make pretty well even ball bearings. So if I want to slide these two surfaces, surface A and surface B over here in two different directions, one in, let's say, this direction, one in that direction, over each other, it's kind of gonna roll a lot easier and slipperier than the previous one, where you have different sized molecules that are there. It gives you kind of a bumpier road. So this is again a very simplified reason of difference between mineral oils and synthetic oils. So in basic oil blending and understanding additive reconstruction, it does require a basic understanding of how lubricants are blended. So in the following 5 slides, it's again a very simplified way on how lubricants are blended. Not going into anything technical, but I think it's something that everybody can pretty easily understand. So the first thing you do is, that's slide number 1, you find some drums, if you're going to put them in drums or totes or pails or whatever you have over there. So you find some drums. Then you fill them with either a base oil, mineral oil, or synthetic oil. After that, this is your mineral oil, this is your synthetic oil. You throw in some additives. The additives, of course, have to be compatible. You can have antioxidant, anti-wear, extreme pressure, rust inhibitors, all anti-friction, dispersants, whatever you want to throw in it, whether it's a motor oil, hydraulic oil, or whatever, it goes into there at basically at that point. Step number 4, mix them and label them. Pretty easy to do. And then, of course, maybe 4 and 5 slides should have been switched around, but you do some QC checking and you make sure that the product meets the specifications before it goes out onto the market. So what happens after it goes out on the market and it's there? Well, if you're a huge oil company, you want to sell lots of oil and you want your people to change the oil every 5 minutes or 50 miles or whatever you want to do. But if we're going to be conservative and want to think about reducing our dependency on primary resources, so it begs the question of, can we treat a lubricant to increase its service life? So here's a new oil, okay, and over time it becomes an in-service oil, or could be a used oil down. Can we not reverse and make this work, make this last a little bit longer? Because as I said before, the base lubricant that's in there is already hundreds of millions of years old. How can we make this last longer, and how can we make this air compressor keep working with oil that's lasting longer and longer in there? So the answer is yes, of course we can do it. What we can do is and I'm sure a lot of you are familiar with Test Oil's analytic capabilities. They have a very impressive laboratory with lots of equipment, and one of them is what we build, which is called a COAT system. COAT is Continual Oil Analysis and Treatment System, and it's an FTIR. It's a Fourier transform, infrared-based spectrometer that we can look inside the oils, we can diagnose the oils, and we can take a look and we can see what's happening with the additives that are inside. Now, in the introduction, way back when, we were talking about we do work with other types of products, not only petroleum, but the diagnostic tool is to look inside and see what's inside. Whether you're doing wine and booze analysis, blood analysis, urine analysis, kidney stone analysis, different polymers analysis, the infrared spectrometer is a great tool to get inside and see what's happening to components in a system that you have. So I'm going to just give you a real quick synopsis on the FTIR and how it works and the whole concept of additization through FTIR. So the FTIR is a precision validation. It's very reproducible. It's non-subjective. It doesn't depend on somebody finding an endpoint or somebody looking at something and determining a color number. It's very instrument dependent, and it has a high information content. So we basically look at, you can have an absorbance of how much light is going to absorb a curve on one side over here, and at what wave number you're going to have. I'm going to go into this a little bit further. Don't get bogged down with this if you don't understand it. There's a few slides that are coming up that is going to explain this pretty easily. I would think so. So in basic FTIR oil analysis, so understanding the additive reconstruction requires the understanding of how lubricants are analyzed. And again, the next few slides, we're going to basically show graphically what we're doing and how this re-additization comes into play. Let me just click over here. Okay, so looking at FTIR by itself, okay, the FTIR provides a fingerprint of the oil which is created by its distinctive additive package, its contaminants, and its breakdown products. So we can detect soot, oxidation, antioxidant levels, anti-wear, fuel dilution. We can also find out if it's the incorrect lube. This is a huge, huge issue, by the way, for commercial laboratories, making sure that the right oil is in the right gearbox and nobody's mixed the wrong oil inside. And incredible amount of stories that I've seen over the years with incorrect lubes in there. Ester breakdowns, sulfate byproducts, glycol contamination. You can do acid number, base number, moisture, and nitration. These are just some of the parameters that you can determine using FTIR. So looking at the FTIR, this is basically a sample cell. So you pump your oil, comes in here. There's two windows that are precisely, let's say, 100 microns spaced apart from each other. The oil comes out over there, so it's a pump that just pushes this in and out of the cell. This cell can be temperature controlled for fuel dilution, there's a lot of different parameters that can come out of it. But basically, you're going to get this spectrum that's going to come out. And fortunately, we don't have to sit down and take a look at this and look up books and see what's going on there, because these computers now, and I'll tell you, even over the last 5 years with the speed of PC computers, it's incredible how much information can be stored in there. So if we actually look at that little graph that we have there, we know that different parts of the spectrum have different information that's out there. You have fuel information over here, you have glycol sulfation. But what we're going to do is, just moving forward, okay, we're going to just concentrate, because otherwise we can be here for all week. We're just going to concentrate on this little peak over here, which is an antioxidant. All right, and we're going to just follow this little peak for a while, but keep in mind this can be anything else that's down the line. So there we go. We're just going to look at the peak positions, and we're just going to talk a little bit about antioxidants. Now, we can manipulate spectrum the same way you manipulate numbers. We can take a spectrum, okay, we can minus the same spectrum and we can get a flat line. Or we can add the inverse of the spectrum and get a flat line. It works pretty well mathematically, and this is what we call spectral subtraction. And for those of you that are doing trending, we basically have your new oil over here minus your used oil over here, and then we get some sort of differential, which is going to lead us up basically to the next slide. So we're looking at our little oxidation peak that we had over here, okay? And over time, this oxidation peak is, sorry, not the antioxidant peak, not oxidation, sorry. So this antioxidant is going to be depleted, so this peak is going to get lower and lower and lower. And this could be over, you know, 5 years, 10 years, or 20 days. It depends on what the severity is. Now, if this was, as in the previous slide, exactly the same, you're going to get a flat line. But if this peak is going down, then you're going to have this flat line over here. In that area, you're going to have this antioxidant depletion. And you're going to be able to track this antioxidant depletion. And for instance, this lowered peak over here would be a little blip over here. As it goes lower, this little blip gets even pointier and pointier until you're almost out of antioxidant, and it comes down to a very low peak at this point over here. So let's take this data that we have now and graph it. Okay, so we blew this up over here. This is our antioxidant from day one that we have over here. This is in the new oil, let's say. Okay, and then over time, this antioxidant goes down, and we track the depletion of the antioxidant over time. Again, your x-axis can be years and it could be days. It depends on your equipment, the temperature of operation. But now we beg the question, so what happens when we lose our antioxidant? So what happens? Well, let's take a look. If you've seen from your oil analysis reports that you have there, when we start losing our antioxidant, our viscosity is going to go up. So if it was 32, let's say this was a 46 in the middle, you start losing it, your viscosity is going to go up, and most importantly, your acid number is going to go up. When your acid number goes up, you become very corrosive within your equipment itself. And sometimes at this point over here, your people doing your analytical work at test oil will say, well, it's time to change the oil because you can't have this over here. You got to get this. You got to get this down. But what if we take another approach and we say, okay, we're not going to change the oil. What if we decide that we're going to throw in some more antioxidant at this point, right over here? We're going to kick this off at the pass. The antioxidant is added. again, we have to watch everything else at the same time. Your water contamination, if you have soot that's coming up over there, your soot may be your limiting factor. There's always going to be a limiting factor that's going to determine the life of your lubricant. And we don't want it to be the depletion of antioxidant. We're going to try and shift this to something else. So we're still watching the water and the contamination and the soot and the dirt and the metals in spectroscopy. These are things that always have to be watched. So we throw in some antioxidant there. So what happens to the curve? Well, we added the antioxidant back in. We're not allowing the viscosity to go up anymore because we have the antioxidant back in there, so the viscosity kind of equalizes off over there. And the acid number also seems to level off at the pass. So now your curve looks more like this. And then again, down the line, what stops you from adding it again? Now, in a lot of work that we've done over the past 5 or 6 years, and we're servicing mines all the way up to the Arctic and the North Pole and in different areas, we've been able to quintuple the life of oils just by re-additizing with, well, in this case it's an antioxidant, but we've done anti-wear and an EP and other additives. So what you're looking at over here is, okay, let's watch what's doing. Again, we don't know what the time factor is between this and this over here, but why not? If everything is going well, why can't we maintain it? It works. It's a concept that is something that was not available 10 years ago because we didn't have the computer speed and the technology to do it, but now we can do it. And I know that people are going to ask, they're going to say, well, how do we know what the level is? We're going to talk about this, or if it's the right antioxidant. I hate to use this terminology, but it's like either you're pregnant or you're not. So your oil is going to be either inhibited against antioxidants or not. The infrared spectrometer scans all the possible antioxidants that are in the fluid itself. It knows, with your viscometer, if your viscometer is going up, and it also tracks your acid number. So you're increasing an antioxidant, even if it's not exactly the same antioxidant that's in the original oil, it will inhibit it at the same time. Now, this is something that we can discuss on another venue, but it's a little bit out of the scope of this talk today. But now we talk about parameters, okay? When do you want to start? At what point do you take this antioxidant peak over here? This being the original new oil, okay, here's 95% because we've re-added it back in again. We determine what a critical minimum level is, and that critical minimum level can kind of move around a little bit depending on how the acid number and how the viscosity works within the fluid itself. And it was triggered when the level was at this point over here. When it gets down to here, it could be a little bit too late because, again, your acid number is your aging of the oil. It's like the fountain of youth. Now, I know you cannot reverse the acid number in mineral and most synthetic oils. There's some phosphate esters, of course, that you can do it through some filter medias that can be reversed. But in generalities, after a certain point, then you're at the point of no return, and then it's time to change the oil that you have. So this is actually a data sheet that was done. Sorry, it's metric for those that don't understand metric, but anyways, it's the gearbox capacity. So when we sort of got in over here and getting up to about 1,000 hours, there was the antioxidant was re-added back in, and we were able to basically stabilize the product going forward. We've had many instances where we're able to get up, to over 100,000 hours in some large hydraulic systems by just servicing and re-additizing the fluid. And these are, from power stations and hydraulic units that have thousands of liters or hundreds and hundreds of gallons of reservoir. So just thinking of the saving in disposal costs and downtime is pretty impressive. We're going to come to a slide just a little later with this over here. So these are basically the reconstructive additives that you can put in. You can antioxidant, anti-wear, EP, even the VI improvers. Sometimes you're using high VI oils and they'll shear down. Well, you can add more. It requires, all of these require calculation on the size of the gearboxes. Pour point suppressants, tackifiers, defoamers, corrosion and rust inhibitors, dispersants, detergents, even a tracer dye. Some of these things, they just wear out or are used up after a point in time, and they can be put back in. There's no reason why they can't do that. But there are limiting factors, and the limiting factors are quite substantial. Of course, wear debris, soot, dirt, water, condensation, alignment, vibration, wrong oil, leakage, evaporation, foam, fuel contamination. So there's some things you just can't avoid, and at that point it's really a waste of money if you're going to look at additive re-additization because of these limiting factors that you have here. So if these can be corrected and they become your limiting factors, if you're have problem with evaporation and you can now change the filler cap or breathers and put something that's more durable that's on over there, well, you can extend it even further. So this is the whole idea of what you have. And ultimately you can put an online FTIR onto a system, and this is our COAT, which is, as I said, continual oil analysis and treatment, that will automatically add your additives back into an oil reservoir just through a little kidney loop into the system and back. And this is something that Test Oil can work with you on. Test Oil can do the analysis for you. They can offer the additives. We're working with them on setting this up on how to do it on basically a gearbox or reservoir by reservoir system, because the amounts have to be calculated in over there. But it's something that they are very well set up and very, very well able to handle going down the line. So the last is the cost of ownership. And this is something that I get a lot of, there's a lot of difference on it. And there's a total cost of ownership because these additives are not cheap. When we look at the cost of ownership, and we basically have to look at something that kind of looks like this, okay? You have a particular gearbox, you know the volume. This is all done metrically. Again, of course, it can be put into anything that you want. Hours of operation, oil changes, operations per year, how many oil change interval in hours, the top off. If you're going down over there, then you take your delivered price. Now this is a conventional. These are actually figures that work. Okay, we're looking at dollars per liter. Okay, and here we're looking at a synthetic dollars per liter. Same gearbox. Here you're talking about a top off, let's say, of 3.5 liters that they're going to add in between oil changes. And here, this here, let's say 1.5. It's still the same 3.5 liters, but you have 1.5 liters of the oil, and let's say 1 liter and 1 liter of 2 different additives that go in there. Price is synthetic of, let's say about double the price of the conventional oil. And this is your price of your additives. They're pretty expensive. So your cost of oil analysis stays the same. I hope Test Oil doesn't sweat with this here, because I don't know what they charge, but I think this is a reasonable one. You have your disposal. Disposal is the same. It could be more, and you also have your warehouse costing of how much inventory that you have of your lubricant that you're keeping. And this is obviously going to come up more expensive. You're more. So it may take 2 hours to do an oil change. Still may take 2 people to do the oil change. Average labor cost that you have over here per oil change. And because on this here, the reason why this is less here is because here you have 300 hours between oil change, because you're monitoring this with your additives that you have in over here, and this is just a 50% increase in oil change intervals. Your annual labor cost per oil change is down. So your lubricant cost may be up, your labor cost is going to be down. Repairs and maintenance will also be less if you're doing less oil changes. Of course, the cost of purchase orders, the purchase orders per year, if you're ordering less, whatever. So if you take a look at this analysis over here, so you can be spending more money on the oil, but you're still saving about 9.2% per year over convention. So looking at cost of ownership is very important to get all the parameters that are in there. And there may be more parameters that are involved that are not even addressed at this issue here, but it's important to get this side-by-side cost of ownership of really what does it cost to maintain your equipment. So to conclude, okay, just to recap over here, the additive reconstruction, it increases domestic economic stability, believe it or not. It reduces dependence on foreign supply. It goes hand in hand with good machinery maintenance. It significantly reduces demand on primary resources. It reduces fluid inventory, reduces disposal of used lubricants, which is now waste lubricants, and it usually doesn't require equipment shutdown if you're re-additizing. It just may mix right into the reservoir or expansion tank itself, and most cost-effective form of lubricant life extension. Thank you. That's it. Did that in 45 minutes. I can take a few questions if there are.
Well, thank you, Dave. That was a very interesting presentation, and we do actually have 2 questions. The first one is, have you used the ruler method to measure remaining antioxidant levels in used oil?
No, we haven't. The FTIR is actually a lot more accurate and a lot more predictable than the ruler. It's also, buying an FTIR is more expensive, but I have not used a ruler.
Okay. The same person asked another question. Do you ever see stability issues, meaning dropout or precipitation, when re-additizing used oil?
No, we don't, because I know where that person is coming from, and that's an excellent question if there's some incompatibilities. But the incompatibilities of additives, normally we know through the FTIR spectra how it's tracing, and we know really what's compatible and what's not compatible. It's not really a major issue in re-additization, if that answers the question.
Okay. We do have one more question that we can fit in. Have or can you miniaturize the coat FTIR for automotive applications?
Sorry, can you repeat that?
It says, have or can you miniaturize the coat, the COAT FTIR, for automotive applications?
if I understand this correctly, this is to put it in a car engine. That's a very interesting question, because a lot of the newer cars now do have these indicators of when to change the oil. They really don't have anything to do with the oil itself. You can fill your car with milk, and you're going to get the same algorithm. The algorithms that they use are basically how many starts and stops, and you know, the outside temperature. It does take in a lot of data, but as far as I know, they don't actually measure the lubricant. And one of the reasons why they don't measure the lubricant is that it's very difficult to keep the sensors clean. Once you start building soot in an oil, you can't open up your engine and clean the sensors to do it. So keeping the sensors clean is really, really difficult. And this is something that has to be overcome down the line. But technologically, you can put a sensor in there, but keeping it clean and you know, getting viable data is probably on the horizon, but not there yet. But that's an excellent question.
Okay, we have a couple more questions that are coming in. But before I ask one, Mr. Murray, could you re-ask your question? I'm not sure if it's in a question format or if you're making a statement. And then I'll move on to the next question and come back if you're able to reissue that question. The next question, Dave, is there a capacity of oil that could be considered a candidate for additization?
The easiest ones to additize are hydraulic oils and gear oils, because of the fact that they don't have too many additives in them. Those are the easiest. If I'm understanding the question correctly, those are the easiest oils to additize at this point.
Okay. It looks like the other gentleman's question, I'm waiting to get a reissue of that, but I think being the time is we're getting close to the end here, I'll ask if it's okay. Mr. Murray, we will ask that. Oh, here he goes, here he goes. Instead of having an EP or AO or viscosity improver, just a new oil. Let's see. He says using new oil of same manufacturer to sweeten the oil instead of separate additives. Instead of having an EP or AO or viscosity improver, just add new oil. I'm sorry, I'm not sure if he's asking a question.
I think I know where he's saying. I mean, yes, you can. A top off would be good, but you know, will it? I mean, if the oil that you have in there, let's say, antioxidant depleted 75%, and you have, let's say, 100 gallons, and you want to add 1 gallon of new oil to it, it's not going to make much of a difference of the, you know, now you have 101 gallons of oil, where 100 gallons has lost 75% of the additive, and you have 1 gallon that has 100% of the additive in there. It doesn't really add much to what's in there. So yes, it's a possibility, but depending on how much oil you're adding in there. If you recall, one of the limiting factors on the limiting factor slide was leaking. I mean, if you're leaking and you're constantly have to add new oil on top, well, this is not the right venue to do it, because your new oil will be replacing the old oil that's in there. But you know, depending what the proportion is, it doesn't make it doesn't seem to be. And again, if I understand the question correctly, that doesn't seem to be the right way to go.
Okay, Dave, can you clarify one of the previous questions? The gentleman is re-asking, could you define what the quantity of oil that would be considered as a candidate for additization? So his example is 300-gallon capacity, 50-gallon capacity. what would be your guess on that?
Well, if you're okay, if let's say a test oil customer, if they're doing oil analysis on a 2-gallon gearbox or a 3-gallon gearbox, that's fine. That can all be put in there as long as the data is there. Proportionally, additives can be added in. We've done re-additization on gearboxes that are, 3 or 4 or even 5 gallons. We've done it, and these are companies that have hundreds of gearboxes, and we've put it in there. So we basically give them a bulk tank, sort of, and not a bulk tank. We can give them containers of. Let's go back and just use this antioxidant just for the sake of consistency. We can give it to them, and we will tell them based on the data that test oil would have doing the oil analysis. We will say, okay, put 3 ounces into this gearbox, 4 ounces into that gearbox, and 6 ounces into this gearbox. So it doesn't really matter the size of the gearbox at all. I hope that answers the question.
Okay, thank you so much, Dave. We're getting really close on the end of time here, so I'm going to go ahead and close the webinar. But I wanted to thank Dave for presenting today, and thank you everyone for attending. Shortly, you'll be receiving an email with just a few survey questions. If you would please answer those, we'd love to hear your thoughts. And then if you're interested in receiving a recording of this webinar or any of the presentation slides, please send me an email. That's kwilliams@testoil.com, or you can just reply to the emails that I've sent you. Thank you very much, everyone, and y'all have a great day.
Thank you, everybody, for spending an hour with me. I really appreciate it. Thanks a lot.
Thanks,
Bye-bye.
Dave. Stay warm.